All right. Chapter 8, Day 6 video. We're looking at how do we use logs to solve exponential equations. We've solved some exponential equations before, but that's because they were set up for us to solve them easily. But now, not all problems are set up easily, so we can solve any exponential problem after we learn what we learned today. So first of all, let's recall something. The undoing of an exponential is taking the log. The log undoes the exponential. Just like the square root undoes a square, or a square undoes a square root, the log undoes an exponential. And so that's how we're going to use logs to help us. So for example, the problem might say, solve for x. 4 to some power is 12. I can't think of a power on 4 that equals 12. Now, you might say, well, let's rewrite it. Don't write this, just watch for a second. I could rewrite this, log base 4, and I could trade these two. But here's the trouble. I still have no way to get this answer. It's not something that works out nice in my calculator. It's not something that works out nice in my head. I can't think of 4 to some power and I get 12. And so because of that, we're going to take the following approach. We're going to undo this by taking the log. Now, just like when we took the square root to undo a square, you have to do it to both sides. So when you see an exponential problem and your variable is the exponent, you can undo that by step 1, take the log of both sides. So, take the log of both sides. So I have log, again, now we're on base 10. I'm not going to write it. Log of 4 to the x equals log of 12. I take the log of both sides, which means just put the word log in there. Just like when we took the square root of both sides, we wrote square root, we'll write log. Okay. Now, use the re-expression property for powers to move the exponent in front of the log. All right? So, our re-expression property of powers says I can rewrite this and move it out front. If you remember day 3. So, x log 4 equals log 12. All right? Now just divide out, or whatever opposite operations we need to get x by itself. So I'm going to divide out by log 4, divide out by log 4. So step 3, solve what is left for x. And lo and behold, x is, that's just the readout from the calculator. If you notice in the problem, there was no rounding directions. And in your test, if there's no rounding directions, you have to write out the full calculator display. You cannot round just because you think it's convenient. All right? So again, I see a problem with an exponent. I undo it by taking the log of both sides. So I move the x out front. Divide out by log 4, and I'll have x left. And that is how we solve exponential equations. Let's take a look at one that might be a little bit more difficult. All right, so what if this exponent piece isn't isolated? Well, the first thing we're going to do is isolate it. So I'm going to take away 6 from both sides. 3 to some power is 11. Again, I don't know what that is. I mean, if this said 27, then I can do that in my head. But 3 to some power is 11. Well, I'm going to have to take the log of both sides. So when I take the log of both sides, I can just pull this out front. So x log 3 is log 11, using my re-expression property and pulling it out front at the same time. Divide by log 3. And x equals, what do I have left? 2.18, all that from your calculator, okay? Sometimes the exponent might have a fraction in it. It doesn't matter. It's still the same type of problem. In this one, we're going to round to the nearest tenth. So I got to take the log of both sides. But again, this whole part's going to come out front. So x over 2 log 13 is log 25. Divide by log 13. All right. And I'll have x over 2 is log 25 over log 13. How do I get rid of the 2 on the bottom? I multiply both sides by 2. So log 25 times 2 divided by log 13, and my answer would come out to be 2.5 to the nearest tenth. So watch your rounding directions, because they usually will give some. But that is, the basic part of solving exponential equations with logs. The application of it, here's a problem that we would do with that application. This deals with carbon dating from like archaeology and that kind of stuff. So, for example, carbon-14 dating is used to determine the age of a substance by using the following formula. A equals A sub 0, we write that as A sub 0, 2 to the power of negative T over H. I know it sounds and looks very fancy, but don't worry, we're going to be okay with it. And then they define the pieces, where A is the amount of carbon-14 the specimen has now, A sub 0 is the original amount, H is the half-life. Half-life is given usually from some chart. If you're in the class dealing with archaeology, if you're dealing in this class, they will tell you what the half-life is. And T is the time in years. All right? So question A. Find how old to the nearest 100 years a substance is that originally had 250 milligrams of carbon and now has 130 milligrams of carbon if the half-life of carbon is 5,760 years. So here's a situation that they run into. They want to figure out how old is this item. Well, you have to identify all of the pieces according to this. The amount that it has now. The amount that it has now, 130. The original amount, 250. The half-life, 5,760. So I identify all of those pieces. And now we just plug and chug. So I plug into the formula. All right? Here's my formula. A equals A sub 0, 2 to the negative T over H. So A equals A sub 0, 2 to the negative T over H. A, which is the amount we have now, equals A sub 0 times 2, that number was in the problem, negative T, that's what we don't know, so I'll put an X there, over half-life, okay? Well, just like the previous problem that we did, in which this was not isolated, this problem here also deals with a situation in which this number that's being raised is not isolated. So I want to get rid of the 250 to begin with. So I'm going to divide out by the 250 first. So 2 to the negative x over 5,760 is 130 over 250. Okay? Now, how do I undo the exponent? I take the log of both sides. All right? So I'm going to take the log of both sides. So I got 130 divided by 250 is 0.52. All right, so this is really equal to 0.52. All right, so I have taken the log of both sides. The log of 0.52 equals, this comes out front, negative x over 5,760 log of 2. Taking the log of both sides, so I divide out by first, take the log of both sides. Now, opposite operations. I'm going to divide by log 2, divide by log 2. I'm going to multiply by 5,760. I'm going to multiply by 5,760. And when I do that, I get negative x equals negative 5,434. Well, I'm going to multiply both sides by negative 1, so it makes them positive. And the direction said to the nearest 100 years. So 5,434, nearest 100 years would be 5,400. So we could say that this substance is 5,400 years old. And that's the application in like a word problem or a real problem of solving exponential equations using logs. That's it.